Okay, we are recording. We're now moved into section 11.1, functions of several variables, multiple variables. So we have seen this back in section 9.6, functions of several variables. And a good example, why do we, so like in calculus 1 and 2, you dealt with functions of one variable. But why do we need functions of two variables? Well, for instance, wind chill, to model wind chill appropriately, we need to recognize not just temperature, but also wind speed. And they have a nice table here in the book that shows you table-wise how wind chill, how wind chill is clearly a function of air temperature and wind speed. So if you look, for instance, where the air temperature is 5 degrees, okay, air temperature 5 degrees Celsius, and what happens as you go across the row, where T equals 5, as you go across the row, the wind temperature, the wind speed, I should say, the wind speed's getting greater and greater. What's happening to the wind chill index? What happens to the wind chill index? What's happening? Is it getting colder or is it getting warmer? If you hold the temperature at 5 degrees Celsius, and so in this table, and you move across, what's happening as the wind speed increases? What happens to the wind chill? That's right, Ivy. It's getting cooler. I mean, look, when you're at 30 degrees wind speed in kilometers per hour, the wind chill's zero degrees. Okay, but then when you go to 40, when wind speed increases to 40, you're at -1 degrees. Okay, so and basically that's the pattern across every row. Now, if you look vertically, let's say you hold the wind speed constant and decrease your air temperature. So if the velocity, let's look at that first column. If the velocity is 5 kilometers per hour, okay, as you go downward, you're decreasing the temperature, okay, the air temperature. What happens to the wind chill? What happens to the wind chill? Is it getting colder or hotter? So look at the first column there in the table, where where wind speed's 5 kilometers per hour. And if that's held constant, but the temperature gets less and less and less, the actual temperature, what happens to the wind chill? That's right, Norina, it's getting cooler. So you see, you can't model, very good. So you can't model wind chill really just as a function of one variable. You need two variables. And this is why we need, multivariable calculus. Now, there are a lot of other applications too. A lot of other applications. Another application is something called the Cobbs-Douglas production function. Okay, I don't know if any of you are majoring in economics, but the Cobbs-Douglas production function says production is a function of labor, okay, the amount of labor, okay, and K is the capital invested. So if you increase your labor and you increase the amount of money you put into the factory, you can produce more. Okay, that was the issue, right, with the issue with the baby food, right? There's when they close the factories, you don't have labor. So it doesn't matter that there's a lot of money in the company. If the labor's not there, you're not going to get any baby food, right? So I mean, this is a relevant, no baby food will be made, right? So this is another example of a relevant model where you need a function of several variables. So, okay, so, but we go a little deeper into understanding functions of two variables. We already talked about domain and range for functions of two variables, but visual representations is where we go a little bit deeper. Okay, so in example 4, and I'm going to leave this highlighted because I like it there, they want you to sketch the graph of this function, this surface, that's the square root of 9 minus x squared minus y squared. Well, how would you do that? What you can do is you can let z, let g of xy equals z, and then square both sides of that equation, and you'll end up with x squared plus y squared plus z squared equals 9. That's the equation of a sphere with radius 3. But it's just the top part because z is positive square root of 9 minus x squared minus y squared. Okay, so we can do very simple kinds of functions, look at surfaces, but sometimes the surfaces get a little more complicated. So how do we deal with those kind of situations? Well, okay, so we have something called level curves. Level curves. So hold on, let me get this centered. So the level curves of a function of two variables are curves where you set the function equal to a constant. So in other words, the z value is constant. Okay, so you set the function equal to a constant, and you get what are called level curves. So, like, for instance, we have some examples of that here. If we look here in figure 4, okay, there is a function, a surface, a function of x and y. And, it is a function of x and y. If you think about, like, remember functions, yeah, it's like the UFO. And you see on this figure, figure 4, it is figure 4, you see how they are cutting that surface, that UFO-looking surface. They're doing horizontal cuts, which are like horizontal traces. They're doing horizontal cuts. And what can you tell me about the space between each of those horizontal cuts, those blue horizontal circular cuts? What can you tell me about the space between each of those cuts? Is it the same? Or is it different? That's right, Yeva. It's the same. And you see what they do there. If you take those cuts, so like in the XY plane, they have drawn what's called a contour plot. That's when you take these level curves that are equally spaced out. Okay, so you see like the level curve k equals 20. That's the bottom level curve, and then the next level curve, look at the red contour plot. The next level curve would be k equals 25. So the level curve where k equals 20, that means you're setting f of xy equal to 20. And then all the xy coordinates are there. They have to satisfy that circle or ellipse. So basically, you see the idea, it's just sometimes it's easier just to look at the picture. But in order to understand, I mean, if you were to look at the contour plot in red on the bottom of in the XY plane, could, based on that contour plot, you visualize the surface? Because that's what the contour plot is. The contour plot consists of level curves of the surface where you're skipping by, in this case it's 5. you know, your K equals 20, K equals 25, K equals 30. You're skipping by 5. Okay. If you were to take those level curves, could you then visualize the surface? Okay, that's a common kind of idea. They have another example here of, I don't know if you've ever seen these kind of maps, but here you have a topographical map of a mountain, Lonesome Mountain. How many have maybe seen topological graphs or topographic graphs like this, or pictures? IB has, okay. Yeah, you know, I mean, pilots certainly would be interested in this, right? Alberto has seen it, okay. Lexi says you use them all the time. Lexi, where do you work, if I may ask? You use them at your place where you work, or at the consulting for the USDA? Okay. So Lexi's seeing them at the USDA for farmland. Okay. Well, you see the level curves, they have different level curves that show elevations of Lonesome Mountain. Now notice that when the level curves are kind of close together, what's that tell you about the mountain? Is the mountain steeper or shallower when the level curves are kind of close together? What would that indicate about the mountain? Good, Ivy. Good, Logan. Good, Lex. It's getting steeper. You see, so we can visualize this mountain without seeing the mountain, just by looking at the level curves at the plot. That's called a contour plot. All right, and at the top, you see there's a lot of space between the level curves because you're at the top of the mountain. The steepness has kind of gone away. You're at the top. And this kind of idea is extended also to isothermal plots. How many have seen maybe an isothermal plot with temperatures? I don't know if anybody's seen this kind of graph. Okay, but level curves are important, and you know, we sometimes call these level curves horizontal traces. It's used interchangeably, but you know, they have some nice examples where, like here in Figure 10, here's a graph of a paraboloid that's 1 unit lifted up from the origin. And if you look at the level curves and plot them as a contour plot, you can visualize this surface. As you move away from the origin, the surface is getting steeper because the level curves are closer together. Right? Now, of course, let me just see one thing here. One moment. We actually, yes, I have this in, if you look in MATLAB, so the one thing here though, one thing I will tell you, the contour map on the left, the one thing the contour map doesn't tell you is if the surface is increasing or decreasing. We know as we move away from the origin, the surface is getting steeper, but that could be a bowl going upwards or a bowl going downwards. So sometimes the contour plots, it's nice to put values for the level curves on the contour plot. And what I've done, if you go into MATLAB, there is, let me just see here, I'll bring it up here. Yeah. Hold on here, one moment. Got Windows open, but where? Okay, here we are. Yeah, so if I go, in here. Okay, so I have a MATLAB program that will graph this particular surface, the one for section figure 10, from example 9 in section 11.1. It'll graph the surface along with various contour plots for the surface. So go ahead and open up, click on the link. It should bring the program up, and then copy the code and paste it into the editor. Okay, so you can go ahead and do that. Okay, and this should be what you have. Now what I'll do is in MATLAB, I will use the command clear vars to clear any old variables out. And I will use CLC so I get my command window cleared out. Now don't forget also, class, don't forget also, hold on here. Don't forget also that, I mean, sometimes you'll be presented with maybe a function that how do you type it in MATLAB? Well, if you go to on the command line, if you look under that the symbol FX, click on that, and there's a help menu here. Okay, so you can type in whatever you need, like square roots or absolute values, whatever. It'll give you examples then of how to do those things. Okay, but on that note, so for this particular MATLAB program, let me just get that back here. Hold on. There we go. I'm going to plot the surface, and then I have some different contour plots. Now I want to mention that let me see here. Yeah, I just have different contour plots and different commands. I'll let you look them over, okay? But I will make a comment here. I'm going to make a comment here and here on, and I'm constantly going back to make sure. So when I want to draw 25 level curves, what I do is I'm going to create a mesh grid. Okay, a mesh grid, and the x values, the x range, or think of an x-axis, a y-axis. X goes from -5 to 5, y goes from -10 to 10, and I'm using a skip factor of 0.1. Okay, so, but you'll notice that when I type the z in, I have dots. I have dots like z equals 4 dot times x dot squared plus y dot squared plus 1. When you use the mesh grid command, when you type in your function, you want to use pointwise, what do you call it? It's pointwise notation. That's what it's called. Because remember, MATLAB can do matrix operations. So when you create a mesh grid, MATLAB looks at a matrix of values. But what you're telling MATLAB is, for every point in this grid, every point in this grid that you're creating, please evaluate the function. And you got to use the pointwise. You got to use points before all of your operators, except for plus and minus. So just keep that in mind. I don't know if anybody's ever encountered that in MATLAB. Maybe if you've seen MATLAB before, how many maybe have so like you see the above, if you look above here, if you look above, I'm not using I'm not using any pointwise, like I'm writing z equals 4x squared plus y squared plus 1. but I'm not using any dots before the operators. But it's because I don't have a mesh grid created. But below, in this program, I have a mesh grid key created, and so therefore, when I type my my function, I need to have the dot notation. Okay, are there any questions on that? All right, all right. So what I'm going to do is I'm going to go ahead and run all this code here. So I'm going to let's see here. I'm going to select it all, and you're going to see a lot of different curves here. So I'm going to copy it, and I'm going to paste it in the command line, and it's going to produce a bunch of different curves. Okay, let me show you some of them. Let me show you some of them. So, all right, and how many is this? Is the code working for you? It should work. Okay, so Yeva, you're seeing a bunch of different graphs. It should produce about 5 or 6 different graphs. So, be sure to try this here. Everybody should be participating. Let's take a look at what we got here. So, Windows. Okay, so how many got this figure? How many got this figure? Okay, good. And you'll forgive me, I can't see all the comments just because everything's kind of blocked on my screen. But excellent, excellent. Okay, so let us see what else we can see here. So, all right. So the second figure. Okay, how many got this contour plot? For the second figure. Okay, good, good. But the thing is, see, the contour plot, I'd like to have more level curves. I don't have a lot of level curves here. So let me go to the, let me just go to the fourth one here. Here, well, I have the same number of level curves, but I have numbers on them too. And this tells me, what's this tell me? As we move away from the origin, the values of the level curves are increasing. So is the surface increasing or decreasing? What do you think? It appears it's getting steeper, although more level curves would help to see that. But is the surface increasing or decreasing as we move away from the origin? So the z equals 20. It would be. I assume you're saying increasing. So you're right. If that's what. Hold on here. Let me see. Good, Matthew. It's increasing. IB, that's right. So Matthew, because the numbers are so every level curve. Think of the surface and slicing the surface, okay, horizontally at different heights of the surface. So like where the circle is or the ellipse where 20 is, you're cutting the surface at a height of 20. So that's like the surface. All the z coordinates are equal to 20. And then the next cut is when z equals 40. Then the next cut is another 20 units away, z equals 60. See how it's all equally spaced out? This gives you a frame of reference to tell you that the surface is getting steeper, but also because the values of the level curves are there, it tells you the surface is increasing, right? Steepness could be decreasing or increasing, but the values of the level curves, then they tell you, indeed, the surface is increasing. Matthew, are you good with that? Are you comfortable with that? Okay. All right. Excellent. Excellent. You're welcome. You're welcome. Let's look at the last picture here. So I tried to give you a variety, of different pictures. Hold on here. One moment. One moment. One moment. I might just have to. Let me just close a few windows here. See if I can get that. No, wait, window. One moment, class. One moment. Just have to close some windows because I know it gave. All right, one moment, class. One moment. Let me just run this again. Okay. Yeah. Well, I guess that was the. Yeah. So, you know, um, obviously I can have the graph more cluttered, yeah, but I mean, this is just, but I didn't want it too cluttered. So hopefully this gives you a good feel for everything. And I'm going to just show one more thing from the book here, then I'm going to let you work a little bit. Let me go back to the book. Hold on here. So you see here how you have some interesting surfaces, and then you have the contour plots. Now these contour plots don't have numbers, so like if you look at that first picture in Figure 12, you have two hills and two valleys, but the contour plot, the in the four quadrants, it all looks the same, right? So, you know, um, contour plots are nice, but it's also nice sometimes to have the values of the level curves. And similar situation with the second picture. All right, are there any questions? We're basically, well, I will mention one more thing. I got to do one more here. One more thing. So, oh my goodness. Oh my goodness. Functions of three variables. Okay, so we can have functions of three variables, but we can't visualize a function of three variables except when we set the function of three variables equal to a constant. So in this problem, example 12, they're not saying find level surfaces of the function in example 12. They want you to, I'm sorry, they're not saying find level curves of the function. They're asking you to find level surfaces of the function. And that's because, hold on here, the level surfaces are when you set, hold on, let me just close a few things here. Yeah, the level surfaces are when you set your function equal to k, and x squared plus y plus z plus z squared equals k. That's a level surface. That's a surface, right? And so what is that? That's a sphere. Now, as we change k, the spheres change. And so if we want to get an idea of the level surfaces of this function, okay, we would vary k, and we would get what you see in Figure 13. So this, we can't really visualize four-dimensional space, but how does the surface change? I mean, how does this function of three variables change it changes in this manner. How many think that's like absolutely cool? Okay, Angela's liking it. Aura thinks it's interesting. Okay. Well, good, good, good. Well, Yeva's wondering if it's going to be cool to do. I'll tell you what, I'm going to give you a chance to work on your section 11.1 assignment. I'm going to give you a little time to work on that. So, are there any questions before I stop the recording? Okay, excellent.